This is Robert Sapolsky, and you're listening to Father-Offspring Interviews.
This episode makes heavy use of visual information shown in the full video. Hello, welcome back to Father-Offspring Interviews, episode 67. For our first question, Jose from Argentina says, suppose we are in a factory that works 24/7 and every worker does 8-hour shifts. From the standpoint of occupational medicine, is it better for the workers to shift rotate so that everyone shares the burden of working night shifts every now and then? Or would it be better if there's a designated group that does the night shifts continuously?
Well, first off, I should point out that if we were all hunter-gatherers, this question would be irrelevant, let alone if we were all still Australopithecans, or a malady of modern westernized life, which is the ability to have light on at night, which is the ability to be awake at times that primates like us were not traditionally awake. Okay, I'm going to boldly change the question to instead assuming a 12-hour workday, just to make things a little bit clearer here. So you are getting an appropriate amount of sleep, regardless of when you're working. This is not a question of sleep deprivation. This is solely a question of whether every day you work 12 hours of light, and alternatively, every day you work 12 hours of dark, or in the shifting schedule, if most days you work during the light and then once a week you have to shift your work schedule so that you're on the night shift. And the question is, which is worse for you? Always working at night or mostly working at day, but once every now and then, once a week, having to suddenly dramatically shift and then shift back again afterward? So what we're looking at here is this general topic of circadian rhythms. Everything you could measure in every organ, every cell, every thingy in your body typically has a circadian rhythm, which is to say it's more active at some times of day than the other, and that it's always the same time of day, roughly, that this thingy peaks, this enzyme, this organ, this whatever, that at a certain time of day, it is at peak activity, and then typically 12 hours later, it's at its trough, its lowest level. So you see daily circadian rhythms, and the key thing is different aspects of your bodily function have their circadian peak and their circadian trough at different times of days. Body temperature. Body temperature tends to peak late afternoon, so that 98.6 and oh no, you're running a fever at 99. 99 is actually closer to the norm late afternoon. Daily normal body temperature shifts. In the morning, when you get up, your glucocorticoid levels are their highest. When you go to sleep, they plummet. When you go to sleep, your growth hormone levels are highest. When you get up in the morning, they are their lowest. There's a logic to this. Oh, normally in the absence of major stressors, the most exhaustingly stressful, challenging thing we have to do each day is getting up in the morning and starting to function. Normal circadian rhythm is for glucocorticoid levels in the bloodstream, glucocorticoid secretion from your adrenal gland to peak early in the light cycle and then hit its trough early in the dark cycle. And the same logic reversed with growth hormone. You do your growing at night, go to sleep, dark phase, that's when growth hormone goes up. So the question becomes, how does your body manage to do this? And I think we've talked about in the past, there is a circadian master clock in your hypothalamus, the workings of which are incredibly cool. In addition, your peripheral organs have their own rhythmic clocks going on there that can be commandeered by the main hypothalamic clock. So, two interesting characteristics of our circadian rhythms. The first is called free running. Take someone, put them in a room with no windows, no cues whatsoever about the outside world, and the person just goes to sleep whenever they feel like it, turns out the lights, turn the lights on whenever they feel it. They establish their own rhythm, they free run. And some extraordinarily thorough studies have been done with this, sticking people down in caves for months, volunteers who would decide time to turn the lights out, time for bed, whatever. They would communicate to the surface, the really careful ones, the folks talking to the person down in the cave. It would be using a voice synthesizer, so you couldn't tell whose voice it was. Oh, it's the day shift on the walkie-talkies now rather than the night shift. No temperature cues, no time of day cues. And what you see is your typical person free runs with an endogenous rhythm of about 25 hours. You get the rare weirdos who instead run at a 36-hour clock, or then there's the ones at 48-hour clock, or the profoundly rare ones who were running at a 12-hour clock. But your typical person left with no external circadian cues runs on roughly a 25-hour rhythm. And what external cues, overwhelmingly light, the way the hypothalamus is wired up to our eyes, what light does is it imposes a 24-hour rhythm on your natural 25-hour one. Okay, so the question becomes, what happens to health when you are working awake, lights on, at a time of day when your primate ancestors never did? And what's clear by now is a very large literature, independent of you getting adequate amounts of sleep. If you are getting sleep at a weird time, if you have a major circadian shift, there's all sorts of health consequences. Number one, overwhelmingly, big surprise, there's more accidents for people who are doing night work because you're cognitively a little bit sort of not at your best, and there's more accidents. But separate of that, people who do shift work, night work, long term, bunch of health consequences. Metabolic diseases, increased risk of obesity, of diabetes, cardiovascular, hypertension, cognitive impairment is more dramatic, increased risk of cancer. These are not major effects. These are not, oh my God, the one time I agreed to work the night shift and I am doomed. These are mild effects. Nonetheless, they are impacting your health. So the question becomes, why is it that functioning at a time of day that your species did not evolve to function, why is this bad for your health? And here's at least two models for how this works. Okay, so in this diagram, we see a 24-hour day, 12 hours of light, 12 hours of dark, and we have a very logical setup on day 0, which is the green arrow going upward. The arrow going upward, that is when you have peak levels of the hormones that mobilize energy from the storage sites in your body. Makes sense. That's when you're starting to function. And you could see 12 hours later, at the start of the dark cycle, the orange arrow pointing down, that's when you are having peak levels of the hormones that tell you to store energy away. And your fat cells in your liver, totally logical. You become active in the morning, mobilize energy, go to sleep at night, store it back again. So what we see here is on day 1, you now do a 12-hour shift. You now do a night shift. You shift your circadian clock so that suddenly you are working 12 hours later than you normally did. And the key point is different physiological systems at the body shift at different speeds. And here's a dramatic version. What we see is after having a 12-hour shift, the green arrow is exactly where it used to be. You were still mobilizing energy at exactly the same time of day you used to, but this is now the beginning of your nighttime, and we see that the orange arrow has shifted completely. It shifts within one day. You come back 2 days later, and what you see is the green arrow did its shift immediately. The orange arrow has shifted, 6 hours now. Come back 2 days later, it has shifted another 6 hours. And by day 5, what you see is exactly shifted. Hooray, you're now going to sleep at a different time, and you're storing away your nutrients, orange arrow, at this logical time, and you're mobilizing them, green arrow, at 12 hours later. But note what's going on around day 1. There's a lag time before the slowest rhythm has shifted. There's a lag time where you are now simultaneously giving your brain, your body, a signal to mobilize energy and to store energy at the same time, your foot on the gas and the brake simultaneously. So this is one way in which you would be getting into trouble. Okay, let's look at another example here. And we've got the same general setup here. We got day 1357, and we have a light cycle, and we've got 12 hours of dark, and we've got something that's going on in your cells all the time, which is there's constant little mistakes in your DNA. DNA errors, DNA caused by radiation, caused by carcinogens, caused by everyday life. And what you do then is DNA repair. And as shown in the diagram, we have what is a pretty typical picture for these biochemical processes. It's not just one enzyme that repairs your DNA. It's a whole complex of 4 of them. They're shown in 4 different colors, and they all interact with each other, and they fix DNA mistakes typically during the night. And we see here on day 1, you've got this complex of the 4 of them working together, a great team. And then you do a circadian shift, a 12-hour shift to suddenly doing night work. And what you see is on day 3, only one of the 4 enzymes that work together to do your DNA repair has completely shifted. Another one has shifted most of the way. Another one has shifted a little bit. Another one hasn't shifted at all. By day 5, what you see is they're now all getting kind of close to each other. And it's not until day 7 that they're back again working collaboratively. What have you just seen? When you shift with something like this hypothetical circumstance, half the time you're not able to do DNA repair because the different constituents are peaking at different times. You've got to wait until they all synchronize again. And this might be a pathway by which what's DNA repair good for? Spotting a DNA error that could possibly lead to the start of a tumor growing. And tumor surveillance, a lot of what that's about is doing DNA repair before little mistakes can become problematic. So shifting like this, what you see is, a significant percentage of the time, your DNA repair mechanisms are not working optimally. Okay, so this gives us a sense of why a dramatic shift from your normal hominid sleep-wake cycle could mess up your biology and increase health risks. So the question then becomes, you got 2 options. You can do what would be termed rotating shift work. 6 days of the week, you work during the light cycle. Note this is a job where you're working 7 days a week, so that's the least of your problems. But 6 days, you work only during the light phase. You're 12 hours of work. You do it when the sun is up on the equator. And when it's dark, the other 12 hours you sleep. And now suddenly 1 day a week, you rotate, you shift into working at night. So what does that do? It's obvious. What you're constantly doing is once a week, you're shifting dramatically, and the different parts are taking 1 day, 3 days, 5 days to catch up. And then you shift again, and then you shift again with a pattern like that. If you were constantly shifting like that, if you then switch on day 7 to working at night, instead of now for another week, and then you shift back to day, you only do it for 1 day, you screw up the system even more. All of your different mediators, messengers, hormones, enzymes, etc., are constantly out of whack and trying to catch up with each other. So the alternative then is every single day you do night work. You sleep during the day, you get up at night and work 12 hours. And what you see is, after the first week or so, all the rhythms come together. And in principle, you've shifted the system 180 degrees, but at least all the parts are synchronized now. So in principle, that should be great. 2 problems, though, with that. The first one is no matter how hard you try, if you are working at night and during the day you're sleeping, you're going to get some cues that it's daytime out. It's going to feel warmer, the humidity, I don't know what. Someone will say good morning to you just as you get back to your bunk in your bunker and get ready to sleep and throw you off. You'll be getting more external cues. So you're not purely shifted 180 degrees. And the other problem is, I think most people who do night work, when they then have the weekend, they don't maintain that same rhythm. They switch a little bit back. So they themselves are constantly phase shifting. So in principle, working always at night is better for your health than working long stretches during the day and then suddenly switching to one day of night and then back to day or a few days of night. In principle, this is the worst possible pattern. If you are working at night, the way to make it as healthy as possible is minimize your circadian cues during the day, that it's everybody else's daytime, and stick to that as well on the weekends when you're not working. Because otherwise, you are, just by choosing to not follow the rhythm you've established 5 days of the week, you're pushing the rhythms out of whack all the time anyway.
Next, Harper from Texas asks, what is wincing? Is it autonomic? How does that work?
Well, first off, wincing is one of those words that if you repeat it to yourself, it's incredibly fast that it stops seeming like a real word. So wincing, let me deconstruct wincing, a demonstration here. What's involved in wincing? You shut your eyes and you furrow your brows and you up your upper lip to sort of scrunch your face up, and often you sort of pull yourself in, you involute protectively, or you have the elements of fleeing. What's wincing about it has a lot in common with the physiology of sensory disgust. We know about this. We've covered this in the past. You bite into some disgusting rotten food and there's a rapid reflex where you spit the food out and you close your eyes, you scrunch your face, and wincing is a variant on this, also coupled with protecting your body. What is this? This is like a logical response. If I were to dramatically lunge at the camera now, you might wince reflexively, because what's this about? We've been selected for, like, something's coming at you. Protect your eyes, protect your mouth, protect your facial feet, whatever, and scrunch up, and you wince. You wince, and it is automatic, mediated heavily by both the insular cortex and the amygdala. Okay, so that's great. So that makes sense. You want to cover your eyes, you want to block here, you want to cover your mouth, but this is a logical thing when something's coming at your face. But what about when you go and you stub your toe on that damn chair in the middle of the night and it hurts, and you wince when it's your toe that's hurting? What's the automaticity of this? And I think what this is just some sort of probabilistic wisdom of the body thing. If you're stubbing your toe, couldn't hurt to suddenly do something protective for your most vulnerable parts of you, which is your face, your eyes, your mouth, your ears, that sort of thing. Maybe that's what it is. So that's great. But then it gets more abstract from there. Rather than just something hurtling at your face or stubbing your toe, you remember the time you did that thing that was so embarrassing and so dorky. And when you think about it, you wince. This human abstraction where just looking at something emotionally distressing, emotionally threatening, can evoke the same thing. We've got a special organism here that could have the memory of stubbing your toe or the memory of doing something socially appalling. But now we take it one step further, which is what was that episode? That episode in The Office where Michael had promised all these poor kids to pay for their college, and it turned out he didn't have money, and what was that one called?
Oh boy, yes, Scott's Tots, Season 6, Episode 12.
I think this is generally viewed as the most cringeworthy 30 minutes of television in all of television history, because it's just go watch it, but it's excruciating. And you spend the entire time as he is about to dig himself in deeper and deeper with this massive social faux pas, doesn't begin to approach this. And you sit there and you wince as he now has to get up and say something to these kids when he's just about to shatter their dreams, and you wince over a television character's social faux pas on a massive cringy level. Yeah, we're a very abstract species. Back to a theme we've had a number of times, tapping into disgusting food, cough it out, something hurtling at your face, reflexively protect your face. And now you're reflexively protecting your face when Michael Scott is doing that cringy thing. What do we have? We've got that principle that humans are doing metaphorical stuff with very ancient parts of your body. You spit out disgusting food and you have a reflex involving the insular cortex. And then you do the same thing when you feel sick to your stomach, hearing about something morally disgusting. You activate the same part of the brain. Somebody cuts off your arm. It hurts. You watch a loved one having their finger pricked. It hurts. You feel somebody else's pain with the same neurons, anterior cingulate cortex. There's neurons up there that can't tell the difference between you feeling pain and you feeling the pain of somebody else. Sensory disgust, moral disgust, a warm personality, having literal aspects of temperature sort of processing in your brain. And in this case, we have another one. Ooh, something menacing your most essential facial parts, and you wince and you cringe, and it's awful. And you imagine something awful socially happening to an imaginary fictional character. And just out of parsimony, you've evolved in the last 20, 30,000 years using the same part of the brain that makes you wince when something's hurtling at your face. And somehow there's neurons there that can't tell the difference.
So finally, Aliki from Canada says, would you kindly talk about the hippocampal damage brought about by psychological trauma/PTSD and how to mitigate the learning disability that remains after the PTSD symptoms have resolved?
Well, one of those grim subjects, PTSD, post-traumatic stress disorder, shell shock, combat fatigue, any versions of it in earlier times before it got termed PTSD, and someone has gone through a massive trauma, and in a subset of people, you are left with post-traumatic stress disorder. And we know most of the features of it, a picture of hypervigilance. Somebody, a loud sound, and the person is shocked, has to leap under a desk because the bombs are dropping. Something where a person is hypervigilant to all sorts of social threat, where there's disruption of sleep, where there's disruption of judgment. PTSD can be massively crippling for people who have not gotten help for it. And the question becomes, what's going on with the hippocampus during it? Hippocampus, part of the brain central to learning and memory. So it was in the 80s that a group first at Emory University first reported people with PTSD had hippocampal atrophy. The hippocampus would shrink. Hippocampus would shrink. This was not a good thing. And PTSD is characterized by a lot of memory, cognitive problems of the sort the hippocampus specializes in. And it turned out the more hippocampal atrophy in somebody, the more cognitive dysfunction you would see correlated with that. This was a major important observation. Something about PTSD could cause the hippocampus to atrophy. And the entire literature was based on two study subjects, traumatized victims of combat trauma and traumatized victims of sexual violence. These were the two populations that made up most of the literature. Okay, so you've got shrinkage of the hippocampus. What is that about? First off, you got to have some very, very delicate controls in studies like these. Is it having gone through the trauma that causes the hippocampus to shrink, or is it having developed PTSD in the aftermath of the trauma? And what that's about is only a subset of people develop PTSD after, say, combat trauma. What's the appropriate control group? Individuals who went off to combat, were traumatized, and developed PTSD. First control group, Individuals who went off to combat were traumatized to the same extent and did not develop PTSD. And then a standard issue second control group, people who had nothing bad happen to them at all. So you would have to compare, was this due to experiencing the trauma or was it the post-traumatic consequences? So that's one control you have to do. The other is a lot of people with PTSD develop some sort of substance abuse to try to self-medicate their symptoms. You need to control for that. So after doing these carefully controlled studies, what came through was this observation: atrophy of the hippocampus in people who had had long-term PTSD. What kind of magnitude? Beginning to get in the ballpark of the amount of atrophy you would see with hippocampal shrinkage in Alzheimer's disease, memory problems, dementia there. This was not a trivial effect. So immediately, people who think about the nuts and bolts of the brain, like me, the question becomes, what's causing the shrinkage? Why does the hippocampus get smaller? And there's a number of different models that are possible, or a number of different possible routes. So you got your neurons, and they've got all these long cables, processes, dendrites, axons, axon terminals. An awful lot of the space in your brain is all the wiring stuff, as opposed to just the neuronal cell bodies. So something that got sorted out in the 80s, the lab of Bruce McEwen, Rockefeller University, my thesis advisor, was that sustained stress would cause synapses to disconnect in the hippocampus and dendritic processes, axonal processes to shrivel up. So there was less of the circuitry stuff in between. So that could be a route for shrinkage. Another possibility is there's those glial cells that are all over the place that do support stuff. Maybe they're shrinking, maybe they're dying. Not great evidence for that. Then there was the possibility that with enough stress, enough trauma, you actually were killing hippocampal neurons. And this is what my doctoral thesis was in the early 80s, showing that stress and glucocorticoids could actually kill hippocampal neurons. And then by the late 80s, a whole additional model came through when people rediscovered that the adult brain, particularly the hippocampus, makes new neurons on a regular basis. So maybe what's happening is not so much you're shriveling up neurons that are already there, or you're killing neurons already there, but instead you're simply not giving birth to the new neurons that would be part of the housekeeping. That one has become very problematic in recent years. Mainly because of the fact that it is less clear that the human adult hippocampus makes new neurons, something we talked about previously. Okay, so neuronal projections shriveling up, neurons themselves dying, the suppression of neurogenesis and the shriveling is probably most responsible for the shrinkage. Okay, so what is causing the neurons to shrivel up, or some of them to die, or new neurons not to be born? And it's obvious what the answer is, which is what I've been implying, which is glucocorticoids, cortisol, the main stress steroid hormones that you secrete during stress. And tons of lab work had been showing lots of stress, lots of glucocorticoids, and you could shrivel up the hippocampal projections. You could kill neurons in there. You would suppress the birth of new neurons. Made sense. The hippocampus could shrink in lab animals, including non-human primates. Then there were two human disorders that seemed to be showing the same thing, something called Cushing's syndrome. It's any of a number of different types of tumors where the result is you secrete crazy amounts of glucocorticoids into the bloodstream, metabolic problems, cardiovascular problems. It's like a disaster of a disease. And what was shown was people who had gone 2 or 3 years with their Cushing's undiagnosed, their brains pickled in very elevated glucocorticoid levels, you would see atrophy of the hippocampus. Only the hippocampus, the more severe the Cushingoid hypercortisolism, the jargon for it, the more atrophy, the more memory problems. Major finding, then you go in and you surgically correct the tumor, and over the next couple of years, now the glucocorticoid levels are back to normal, the hippocampus came back to size. So excessive glucocorticoids, hormones released during stress, you would produce something that looked like the hippocampal problems in PTSD, and it was reversible. Second model, people with big time, long-term major depression. And in a large subset of people, that's characterized by elevated glucocorticoid levels. It's a disease of chronic stress, and a literature as well showing over the course of years to decades of unmedicated, untreated depression, atrophy of the hippocampus, preferentially the hippocampus. The more atrophy, the more cognitive problems. The longer the history of depression, the more of the atrophy. Is that reversible when you get somebody on antidepressants? The literature is not clear on that. And at least the first couple of decades of work suggested the hippocampus does not recover from the atrophy caused by long-term major depression. Okay, so this seemed totally straightforward now in terms of applying this to the PTSD model. And in fact, in 1996, I had a paper in Science where, among other things, I said, here's what's going on in PTSD. It's stressful. You went through trauma and you've got this post-traumatic stress disorder. So you're going to have these massively elevated glucocorticoids, and they're going to be damaging the hippocampus, just like in Cushing's disease and in depression. And that turned out to be completely, totally wrong. And this was work mostly done over a number of decades, a group at Mount Sinai Medical Center, other labs since then, showing weirdly, you don't see elevated glucocorticoid levels in people with PTSD. You don't see elevated levels in people who've just been traumatized, just brought into the ER and destined to develop PTSD. You don't see elevated levels. You see lower than normal levels. Whoa, did I not believe that for the first whatever number of times, kicking and screaming into the reality? It was exactly the opposite of what the Cushing's and the depression picture suggested. Lower than normal levels. But then some further work showed something very interesting, lower than normal levels, but the body was atypically sensitive to these lower than normal levels. And work has eventually shown epigenetic changes in glucocorticoid receptors and cofactors for glucocorticoid receptors. So we've got two absolutely opposite teleological stories here. What causes PTSD? People who are not able to mobilize big enough of a stress response during the trauma, for some reason that makes them vulnerable to PTSD. Completely opposite story now. People whose brains were abnormally sensitive to glucocorticoids were the ones who developed PTSD. The field is confused at this point. It's not clear. What's clear, though, is all of this is predicated on one type of scenario, which is the trauma happens, and as a result of the trauma and the post-traumatic period, in a subset of people, the hippocampus now shrinks. What if we've got the carts and the horses all confused here, and it's the people who have smaller than average hippocampi who are the ones who are most vulnerable to PTSD? Again, after combat trauma, after sexual violence, 10, 15, 20% of people come down with PTSD. Maybe these are the ones who went into that trauma with a smaller than average hippocampus and other aspects of vulnerability. All sorts of hints. Who's going to be the subset of people who develop PTSD? People who already have some vulnerability in the system. For example, after 9/11, studies of PTSD family members who lost someone in 9/11, firefighters and such, and within a year, there were two predictors that were very reliable. You were more likely to get PTSD for the same trauma exposure if you were of low socioeconomic status, chronic stress from that, and if you did not have much social support. A larger literature suggesting the same thing, predisposing vulnerability if you had a lot of childhood abuse, if you had all sorts of aspects of childhood adversity, if you had what are termed soft neurological signs in childhood, late developing walking, late developing speaking, bedwetting to an abnormally late age, if there was just sort of problems in the past. And I had this described to me great once. I was visiting the biggest VA hospital PTSD ward in the country. And the psychiatrist who was taking me around, and you talk to one person and he was abandoned at age 3 and repeatedly abused and grew up in foster homes. And the next person was a fetal alcohol baby who was first stabbed when they were 8. And the next person was an alcoholic by the time they were 9 years old. And so I was just, oh my God, these guys. And the psychiatrist said to me, you got to understand, these boys had a lot of mileage under the hood before they ever set foot in Vietnam. So trauma, vulnerability as a predisposing factor to who gets PTSD. It's not that the PTSD shrinks your hippocampus. It's people who have had rotten neurological luck that's produced a small hippocampus who are most likely to succumb to it. So what would it look like if that were the case? There's 2 systems you can study. The first one is when you really, really are both wise and deeply cynical about the impacts of warfare, which is you take a bunch of soldiers who are about to go out to the field into some god-awful situation, and you know statistically 15% of them are going to come back with PTSD and develop PTSD. Image their brains before and after. Look at their glucocorticoid levels before and after. See if there were predictors of something off with the hippocampus, something off with the glucocorticoid system that predicted these are the people who are most likely to get the PTSD. And this was a study which showed that there were all sorts of, for want of a better technical word, just kind of screwy things with glucocorticoid regulation in the brain, like not obviously terrible, not obviously great, just different, just like the system wasn't working quite the same in the people who wound up being most vulnerable to PTSD when they went off to war. This was a Dutch population of soldiers that were shipped off to Afghanistan. So that's one model. Look at before and after, and the mere cynicism that you've got a whole bunch of like special forces guys and you're sending them into hell, and you know 15-20% of them are just going to be shattered by this, and ooh, let's look at their hippocampus beforehand. This is what the science points us to. The second way of testing this was a really interesting study that came out in 2002 in the journal Nature Neuroscience, very prestigious journal. And these guys had a very, very clever experimental design. They discovered 40 pairs of identical twins, where one of the twins went off to the military, had combat trauma, and developed PTSD, and the other one sat at home unruffled. And what you saw was the ones who went off to war and got PTSD, you looked at them and they had hippocampal atrophy relative to guys who were traumatized but didn't develop PTSD, or relative to normal controls. Yeah, the usual deal, the hippocampus was atrophied. Then they looked at the identical twin who never went off to war, and they had hippocampal atrophy also to the same extent. It was a vulnerability trait beforehand. So that was a landmark finding and the strongest evidence suggesting that, yeah, maybe it's the post-period, the stress of it that causes hippocampal atrophy. There's lots of mechanisms from lab animals by which that could occur. But here's one big vote that people who go into a trauma with a smaller hippocampus are more likely to develop PTSD, not people who develop PTSD are more likely to atrophy their hippocampus. Okay, so in principle, this should conclude everything. The jury is still out. This is the strongest evidence, the before and after studies of soldiers, and this one of the identical twin study, the strongest evidence that a small hippocampus precedes PTSD and increases your vulnerability to it, but still arguing for the post period is what's causing the atrophy. At least 2 observations. You take the unimaginable scenario of someone subject to multiple experiences of sexual violence, and what you see there is not 15 to 20% of people get PTSD, 90 to 95% do. and you get the hippocampal atrophy. It can't be that those 95% are the 15% who had smaller than averages hippocampi. What that argues is this is coming in the aftermath. The other observation is the longer it's been since somebody's trauma that they've had their PTSD, the more hippocampal atrophy. In other words, at this point, there's evidence both for preceding hippocampal vulnerability and in the aftermath, atrophy of the hippocampus. And a Harvard group had a nice recent study looking at this and showing there's elements of genetic vulnerability in terms of hippocampal volume. There's elements of early life adversity interacting with hippocampal volume at the time of the trauma. So we had some of before, some of after, some genes, some environment, some who knows what. It's a very, very messy picture, but nonetheless, it is one of the most emphatic ways of getting one of the three remaining humans on Earth who insists that PTSD is psychosomatic, is just malingering, when you show the brain, this part of the brain is atrophied in these people. This is for real. This is real biology. Whether this is the biology of cause or effect isn't clear. So this brings us to the final question. What about therapeutics after somebody their symptoms resolve? I think that was the word that was used. And what about it when you're cured? And my sense, as not a clinician, but spending a lot of time around these folks, is that nobody is ever actually really cured forever of PTSD. Best case scenario, people are able to manage it. People are able to ride out the symptoms. The symptoms become less severe, less present, but the notion of being cured of is kind of a misnomer. What are some of the types of therapies that help people begin to get a handle over their PTSD more readily? There's a whole array of them where some of them are quite controversial, where by all logic they should be making things worse, and some of them really do seem to make things worse when you look closely. There's a whole bunch of medications as well. Antidepressants seem to help lessen the symptoms of PTSD. Benzodiazepines, the minor tranquilizers like Valium or Librium, seem to do it as well. Drugs that block the sympathetic nervous system seem to help. These are drugs that will reduce blood pressure, things of that sort. And that brings up that finding back when I was predicting, people with PTSD are going to have incredibly elevated levels of cortisol, glucocorticoids. And it turned out, no, they didn't. They had lower than normal, but they had very elevated levels of adrenaline, sympathetic nervous system. So a drug that will take the top off that. One urban myth that has to be emphasized is one's PTSD symptoms are not improved with cannabinoids, with marijuana, but sort of viewing this whole picture by now of people with post-traumatic stress disorder, typically now having lower than normal glucocorticoid levels, but enhanced sensitivity of the body to it, give them very low dose glucocorticoids. And that may help. There's a literature beginning to emerge on that.
And that is episode 67. I'm Offspring Chair Sapolsky, and thanks for your continued support of science and the beard.